R16. You have a mountainous location. The boiling point of pure water is found to be 98 degrees Celsius. And how many grams of sodium chloride must be added to 500 grams of water to bring the boiling point back to 100? So this one isn't asking you to predict what the new freezing point or boiling point is going to be, but it's the same type of thing. Okay. And we can do some more, but let's try this one. This one has a twist in it. So it starts with the equation, right? On that equation sheet, which one would it be? Yeah. Delta TB, KBCM. Now, weren't there two choices, though? The ones with the eyes or the ones without the eyes? Is that this one, or is it going to be the one with the eye? With the eye. Because you see what? You see a metal. Sodium. Na, you see a metal. So it has to be the one with the eye. It has to be this one. Okay, now we need the KB for water. Oh, it's not in there. What is the KB for water? I should have my little table out here. Right, I got to give you all those constants. That sounds right. 5.512. 5 point. KB should be 0.512, right? Yeah, for water, its KB is 0.512. Okay, so you're given that. So everyone agrees with this. How many grams of sodium chloride must be added? Are grams of sodium chloride even in there? It's not, is it? What's that? Yeah, we're looking for the grams of sodium chloride. Because it's kind of easy to pick out delta TB equation, but where do you go after that? We could solve for CM. Or keep that equation sheet in front of you. Look at the equation for CM. What is the equation for it? Moles of solute. And remember, just get used to it. When you see moles of solute, that could just as well be what units? You know, the grams, because molar mass. Whether they say moles of solute or grams of solute, it doesn't really matter. So what you could do is you just keep looking at the equation. So you write this guy down, because it was pretty clear to do them, but then just substitute in what CM is too. Just keep going. If it's easier this way, or you could solve for what CM was in the first place, what Jessica's saying. But you could put in here moles of solute over kilograms of solvent.
Solvent's the big one.
Yeah, solvent's always the one they have more of. But sometimes they don't give you both amounts, and they say that something was put in something else. That kind of tells you that what the solvent was. Or it tells you aqueous. That tells you what the solvent was. But right here is our answer. Just convert to grams. Okay. I like, and I strongly suggest this type of way, because you just got to stare at that question until you see what everything is. the question has to give you all of those. It has to. You just got to figure it out. And if you look long enough, you will, because everything else is extra. All you care about is I, kb, and kilograms of solvent. Anything else, and the delta TB, anything else is extra. You don't care. If you look at it long enough, what are all these? Now, do you prefer it? Do you prefer it this way, or do you prefer solving for CM? Which way looks easier? It's the same thing, but I don't know. It really doesn't matter, right? So we need to know what delta TB is. What would you put in for that? It's 100 minus 98. Delta is always, another word for delta is change. So yeah, that's right. How much it changed. So this guy is 100 minus 98 exactly.
So it's
2. Yeah.
So how do you know if it's 98, 100 minus 98 or 98?
Oh, it's always. Think about it this way. Does it matter if you screwed up? If you did, it's always usually supposed to be final minus initial, but it really doesn't matter because if you find out what this is, you say 100 minus 98, or you do 98 minus 100, and you get a negative number, right? If you put in numbers for I, kb, moles, all these guys got to be positive numbers, so it doesn't make sense to have a negative. So you probably just erase the negative sign. Like I, kb, moles, and mass, kilograms of solvent. None of them can be negative. So.
In the question would be also like it's back to 100. So if it was back to 100, would that be?
Yeah. You can kind of think of it that way. I mean, final minus initial, so they want it to be at 100. But delta TB is just how much the freezing point. Sorry, delta TB is how much the boiling point changed by. That's all it really is. And then how we treated it, we didn't really think of it as final and initial. We think of it as, okay, delta TB, that's how much the boiling point goes up or down. Boiling point goes, it goes up by 2. But delta TB is always how much the boiling point goes up. Delta TF is how much the freezing point goes down, right? So delta TB numbers, you always add to the boiling point of the pure. Delta TF numbers, you always subtract from the freezing point of the pure. And that's just something you had to know because the equation didn't tell you. And it had nothing to do with final minus initial. So it's, okay. Anyway, so we had to know that guy's 2. And the little i's got to be 2 again. Oh, and the kb is 0.512. Well, I could write down here 2 has to equal 2.512 moles of solute. Well, I could write, instead of solute, we could write, because what is the solute? Sodium chloride. If you want to keep the word solute in there, that's okay. We have to know the kilograms of solvent, though, otherwise we can't solve for moles. 0.5. Now, I don't know if Gloriana's really comfortable doing this. She sees 500. She just moves the decimal place how many places? 3. And if you get used to doing that, you save probably a couple minutes, and you don't screw up. Because sometimes you I put the 1,000 on top, I put the 1,000 on the bottom, right? If you just get used to moving the decimal place over 3 places. Okay, now you got to do the math. Okay, now to get the math, right, take the 2, divide by this, divide by this, then multiply by that, right? You do it all in one big step on the calculator. All right? The 2 divided by 2, divided by 0.1, divided by everything on top, and then this guy you have to bring over the diagonal. You have to multiply. So the 2 divided by 2, divided by 0.512, times the 0.5, and you get 0.98. 0.98? Okay. But they don't want the answer in moles. They want the answer in grams. Grab a sandwich, Bianca. There's a bunch there. So convert to grams. Right?
That's the moles of NaCl.
Yeah, so you got to figure out what the molar mass is of NaCl. 58.44. Okay. What is this one? I think this one has this. Oh, this one's just turkey. I'm a fan of turkey, so that's all I got was turkey. There's a big one. Oh yeah, I have a bunch of calculators up here if you need one. Now, if you're coming in now, I strongly suggest have this thing out staring at you, right? And only depend on your equation sheet. Don't go digging back in notes and things, right? Because you want to pretend this is kind of like an exam situation here, and no, if you just learn to depend on that equation sheet, a lot healthier. Okay. So the final answer you got to be around 57.2. Okay. So you want to try another freezing point, boiling point kind of thing? All right. Osmotic pressure. Or not osmotic pressure. Preference? Yeah, here's freezing point depression. Okay. .0182 gram sample. Okay. Okay. So have your equation sheet out, staring at you. It's kind of easy. It's kind of pretty straightforward to see which equation to pick. Except molar mass isn't in that equation. Less. So Caroline, what equation are we going to pick for this? That delta TF. Okay. Now remember, there's two of them. Did she pick the right one? Okay. Well, hang on. Oh, you just want to use just the molality equation? There's another choice we have tossed out here. another choice we have. Now, up here, they're after what, though? We're after, I mean, in the final answer, we're after molecular mass, molar weight, molar mass. What's the equation for that? Grams over moles. So I was hoping someone was going to say this one. So we've got a bunch of things to look at here. This is the only one, though, that you have to write down on your own. Right? I'm not giving. That's not. It's really just a definition. Okay. I like to start with this because if you start with what they're asking, if you start up here, you could go off on a tangent somewhere. But if you start with what they want, there's going to be no wasted effort. This is what they want. I suggest starting here, right? And then what would you do if you started here?
Put the grams in.
Yeah. We know what the grams is. All right? They said it was 0.0182. Why isn't it the 2.135? Yeah, it's dissolved in that, and it's the unknown substance. Yeah. Okay. This is all we need. All right. Okay. Now you jump where? Now we need to find moles. Yeah. Here's moles is in here. Right? Now moles is also in here too. If you just substitute in for cm, moles are kilograms of solvent. Okay. So either one will work. Just depends on what they give you. Right? So if they gave us, we wouldn't be using this one because there's no I. Right? It's one of these two. Which one makes the most sense to use? cm. Right? In fact, I don't even think you can use this one because all you know is the freezing point of the pure. You don't know how much it changed by. So you can't even use this one. Even though they gave you CF, you can't use it because you don't know what delta T is. Delta TF is how much the freezing point changed by. So this number went down a little bit. How much did it go down by? I don't know. That's what they have to tell you if you want to use this. So we can't. So we'll have to use CM. But both of these, what's important to realize is these problems can go a lot of different ways. There's so many different ways to write the same question. So you can get moles using this one, realize it, or you can get moles using this one. So both equally valid, just depends on what they give you. So to get moles, it'd just be pretty much a plug and chug, right? Because they told us what the little m is, molality. The kilograms of solvent is going to be 0.002, right? Get used to moving that decimal place over 3 places. Whoop. Let's go down here, this one. CM was 0.0698. Get those moles. And then you said move the decimal place over 3 places, 0.002135. Get those moles. Get comfortable with the diagonal story, right? Cross multiplication. Just leave the moles alone because it's already up on top. So just move the 0.02135 up there. And you'll get the moles. Times 10 to the negative 4? 1.49 times 10 to the negative 4. There's your moles. Put that in with your molar mass equation. And you'll get the molecular weight. I got around 122. But don't go through all that work and lose a point. Grams over moles. Now, while you still have some energy, I say we hit one of those. Remember this? We did not do this in the review. We didn't do one of those determining the rate equations given all those experiments either. Right? So this is what I'm after, this type of question. We didn't hit this in the review. Where they give you a cell length, this unit cell, this crystal, they give you one of its sides. Then they give you the density of the metal. And then they want you to determine the type of crystal lattice. Okay? And these were the answers. You had 3 possible answers here. A lot of work to get it. But let's see if we can remember the answer to R8 first. And then we'll do R9. See if you remember this. How many atoms correspond to each type of crystalline lattice? 1. Oh, there should be a dark one right here, right? 1. And then how many here? 2. Now, why was there a 1 in this one in the first place? Each corner is technically not a half, an eighth. It's an eighth because there's 8 corners. So about 1/8 fits in there in each corner. So since there's 4 corners, and all these have them at the corners, so there's going to be 1 just from the corners. And then you're right, this guy's 2 because he's got the 8 corners, 1/8 each, and then he's got 1 slammed right in the middle, so that gives him 2. So 1, 2, and let's see. Okay, and see all these guys, mark them up. Okay, there's 1. Oh yeah, half here, half here. There's 2, half, half, 3, half, half, 4. Right? Okay. Okay, so that's, you're going to need to know that to finish the question. Okay. So here it is. Lithium. Which element is lithium? Li, yeah. Okay, cubic crystals. Unit cell has an edge length of 350.9 picometers. Okay. Density is 0.534. From these data and the atomic mass, find the number of lithium atoms in a unit cell. Okay. Calculate the number of lithium atoms in a unit cell. Ugh. Okay, how are you going to do this? Change the PM to CM. That's a good one. Okay, and why? Let's do the big game plan here. She's got a good idea, though. We'll change the PM. Here's the big picture. Our game plan. We're going to change the PM to CM. Why? Because of the centimeters cubed, right? Because of this. Now, what is this? That's density. What's so special about it? If we can find the volume of this box, of this cube. Equation for volume of a cube is what times what times what? Length times width times height, but they're all the same length, so whatever we get, we'll just cube it, right? And we'll have the volume. We'll have a volume of our cube. All right? We'll get the volume just by finding length times width times height. So we'll have so many centimeters cubed. So we'll get the volume of it. Then what do we do with that volume? Oh, that's good. And then we'll take that volume times the 0.534 grams per cubic centimeters. This cubic centimeters end up canceling. We get grams. So that's the grams of what? That's the grams of lithium in what? In that cube, that little dinky cube. That's the grams of lithium. Well, if you know the mass of one lithium atom, divide it into here, and we are going to get what, or what? 1, 2, or 4. All right? So this will be the mass. That'll be the mass of the lithium, of all the lithium in, I don't know, that cube that we drew. Right? And so we divide that. So it's either, if we put it this way, it either has to be 1, 2, or 4 Li atoms. That mass, this mass right here of all the lithium in that box, has to be either 1, 2, or 4 lithium atoms. Okay. So that's a big picture. One of the little steps in there is getting the mass of one lithium atom. How do you calculate the mass of one atom of anything? Divided by Avogadro. Divide what by Avogadro? The atomic mass, the molar mass, right? Lithium is 6.941. Divide that molar mass by Avogadro's number, and you get the mass of one of them. Is it on the sheet? Oh, it should be on the sheet. Okay, that's a fair question. I can put it up right here since the test is tomorrow. If I had chalk, in case I forget. Yeah, I'll give you all these constants. .022 to 10 to the 23rd. You can write per mole or mole to the -1. Okay. So see if you can get, okay. Let's go ahead and do this now. We got to get picometers into centimeters. Yeah, 300, oh, gosh. How do I erase? Erase. 350.9 picometers. Now, how many picos? You said it. It was 10 to the -12, right? There's, okay, you can do it one of different ways. A pico is something really, really tiny. So you can write it this way: 1 times 10 to the 12th picometers in 1 meter. Or you could write 1 times 10 to the -12 meters in a picometer. Or you could write this way, if you like. Something that we haven't done much. We probably should have. If I said you had 100, if I said you had 3 centimeters, you can just replace that little c with a 10 to the -2. And then that's really 3 times 10 to the -2 meters. Just replace that little c. So if I just replace that little p with a 10 to the -12 of 350.9, we replace that little p with a -10 to the -12 times 10 to the -12 meters. So there's several ways you can start. with his picometers. Okay. This is, I think this top way is how we typically handle things. But if you remember pico is 10 to the negative 12, just start right here. Then you're in meters already. Okay. But either way works. This is the same as that. Top one's the same as the bottom. Okay, now we're in meters. You got to get it into centimeters. 100 centimeters in a meter. Okay. So we'll have our centimeters. 3.519 times 509 times 10 to the negative 8. Okay, let's erase all this other stuff here. Okay, the next step was, okay, now where we're at is right here, right? We want to get what someone suggested, get that volume and multiply it by the density so we can get the total mass. All right? So get the volume, cube him, get his volume, and then multiply him by that density. So the cubic centimeters cancel, and you're in grams of lithium. Right? So you end up with so many grams. Figure out what the mass of one lithium atom is, divide it into those grams, and you'll get a 1, 2, or 4. You got 2? Did anybody else get 2? I bet it didn't come out to be 2 perfect. Really? Wow. So it depends on how many digits you carry, but usually it comes out to be 2.02 or 2 point something or 1.98, right? When I cubed it, I got that. Let's use the X cube button. All right. Okay. You just take it times itself. Oh, you mean the density part? Oh, I forgot my 3. Centimeters cubed. All right. Okay, the density part, make sure the centimeters cubed cancels. So I have to have the centimeters cubed down there and the 0.534 grams up on top. All right, so the centimeters cubed cancels out. So I get a total mass. That means 0.543? Is that, oh, 534, not 543. Did it again. God, no. 4.32. 23 negative times 0.534. So I get 2.307 or so. Okay. That's the grams of lithium. So 1 lithium atom mass would be 6.941 all over Avogadro. Yeah, 10 to the negative 23. 1.15 times 10 to the negative 23. So we need to divide. Here's the total mass. And there's one lithium atom. So divide those two out, and people are saying we get around 2. If it's 2, the answer should be body-centered cubic. All right. No one's going to eat my sandwiches. I'm going to eat them. Start. Man, they weren't too generous on the meat, were they? Look at that. There's hardly anything in there. Intermolecular forces questions.
On that last question,
Yeah.
when you divide by the 1.15, divided by the 2.30.
Yeah. You have to have those exponents, though.
Yeah, I'm talking about
Yep.
You have to put that 1.9.
Yeah, you divided them wrong somewhere. Okay. We have a request for intermolecular forces question. Yes? 2 is body-centered cubic, because 2 was, you have an eighth at each corner, always, then you have the one in the middle. So that's body-centered cubic. Hey, just there's a sandwich over here for you. Okay. List all the intermolecular forces in order of increasing strength. Identify which type of intermolecular force is present in each. All right. Which of the following would you expect to be molecular solids? Oh, there's one that we haven't talked about. All right. What were all intermolecular forces? London, dipole, and hydrogen bonding. And that's how you list them in increasing strength, too. Right? London, dipole, hydrogen bonding. Okay. Identify which type of intermolecular force is present in each. In this one. Now you want to list the major one. London is always there because stuff is stuff. And stuff sticks to stuff. So London or dispersion or van der Waals, all the same word, same meaning, same intermolecular force. That's always there. So we want to list the major one. In HCl, you would say dipole, right? To get that dipole, you want something really electronegative. And it's almost always one of these halogens. Fluorine, chlorine, bromine, iodine. Because they're really electronegative. Okay. Dipole. Well, you can always list van der Waals. Usually when they say identify all types of intermolecular forces, then they're looking for, okay, then they want van der Waals in there too. Otherwise, they're just after the main one.
And London and van der Waals are the same.
London is the same as van der Waals, which is the same as dispersion. I think that was it. Those three names.
London, dipole,
And this one, yeah, It's hydrogen bonding. Hydrogen with pretty much O, N, or F, something like that. And then we've got this last one. It's just now if you say dipole, dipole, there has to be something in there that's really electronegative. All it is a bunch of C's and a bunch of H's, and it's huge. So it's just going to be dispersion, or London, or van der Waals, whichever one you want to call it. So, yeah, so you have to look in there and see if there's something really electronegative. If there isn't, it's just going to be dispersion. Dipole has to do with this big blob is a molecule. Something in there is a halogen. In other words, the best word to use is something in there is really electronegative. And it's in that group 7A. And then it'll suck up all the electrons to this side, and it'll be partially negative, and it'll make it polar, dipole, dipole. Yeah. But it's a special case if it's oxygen or fluorine. If it's oxygen or fluorine with hydrogen, that makes it hydrogen bonding. Hydrogen bonding is just a super special strong case of dipole, dipole. How about this one? Molecular solid. Pretty much just look through there, find what's a molecule, and that's your answer. What in there is a molecule? And if you remember the tricks to naming compounds, that's also a big hint as to what's a molecule and what's a ionic compound. Ionic compound, we also call them salts because they had cations and anions. That's what holds it together. There's a molecule. And a hint is, one, you don't see a metal. The other hint is there's tetra. And we only counted it in Greek in naming stuff that was molecules. But the best answer is you don't see a metal. You don't see a metal, it has to be a molecule. Do you see a metal? Yep, so don't count him. You see a metal? Yeah, don't count him. See a metal? Nope. It's got to be a molecule then. Okay. And this is the last question I have on intermolecular forces. Range them in order of increasing melting point, from what's easiest to melt to what's the hardest. So you listed what first? What's easiest to melt up here? D. Now, one thing that was big and different was these ionic compounds. And you see a metal, they're ionic. They're held together by, plus and minus. They all have super high. They're really hard to melt. Think of salt. You dump salt on the stove, salt doesn't melt. You have to heat it up really, really high. So those ionic compounds, right? Forget it. You're going to list those last. So that means you got to pick between these two. between B and C, which one would have a lower melting point? So B. B. They both have hydrogen bonding, but this C has that oxygen is much more accessible to those little hydrogens. Okay. So when you see a bunch of carbons and hydrogens, I think of like butter, fats. You know, they melt super easy. Okay. So you'd list B, then you'd list C. Okay, now you have two ionic compounds. D and then A? That's the right answer, but there's a reason. Are, yeah, because of the charges, they're what? Yeah, this one's lower. They're positive 1 and negative 1. Up here, they're positive 2 and negative 2. Exactly. That's why you have to list D and then A. That's the reason for it. Okay. Let's see. How about that rate equation thing? We never did one of those in our review. Here, this thing, right? Yeah, it's just flopping around out there. Those H's can suck up to it. Here, look how hard they got to fight to get in there. And he's already connected to an H. H has got to squeeze in there. Write a complete rate law. So they want the rate constant, the exponents, everything. I got out of place here. Remember how to do it? And we're not sure where to start on this. Start by writing the general rate law. Rate equals K, then in brackets, like H2 to the X, BR2 to the Y, right? Find two experiments where the concentration of either H2 or BR2 isn't changing. And just pretty much divide numbers out. See how things changed. Figure out your exponents. Remember, back. We'll figure it out. Okay. So this, you forgot your K. You need your K. No, on this side, rate equals K times those concentrations. Okay. So let's pick, look at experiments 1 and 3. See how that 1.2 to the 10 negative 4 doesn't change? So for H2, which one's H2? Which one's Br2? All right, well, just write H2 in there. It'll make it easier to remember. We can do it up here. Maybe you're not the only one. Yeah, Monte?
When you find the same right here, I don't know if it's divided by these or these.
Okay. The rate, here, this is the rate. So you divide these two to get the rate, that number.
Okay.
And then divide these two to get, what is this?
X.
This is H2 is this one, Br2 is that one. So divide these two, then you get the Br2.
Okay.
Bless you. Let's make sure. Let me get you started here. Yeah, you can always divide the bigger by the smaller, or it really doesn't matter. If you, for example, if you divide experiment 1 by experiment 2, just always divide experiment 1 by experiment 2. Right? Just be consistent. It'll work out. Or just divide the bigger by the smaller all the time. It'll always work. H2 to the X. Okay, so this is my starting point. That's how I start. Okay? And if I write H2 in and Br2, it helps because it helps me keep track of what's what. So I'm just going to pick, oh, look at experiments 1 and 2. Right? Because look at these guys are the same. So let's do 1 and 2. Divide the two rates. Put that number for the rate. Right? And you divide K by K. You pretty much get 1. Right? If I divide those two rates out, and I agree with what someone said. Just divide the bigger by the smaller. It makes life easier. Yeah, I got 3. When I compare 1 and 2, I get 3 equals, now I divide the two H2 concentrations. Whatever I get, raise it to the X power. 3.6 divided by 1.2, they're both 10 to the negative 4. That's just going to be 3. 3 raised to the X. The Br2 now, whatever I get, raise it to the Y. Here's the two Br2s. And raise it to the Y. So whatever I get, I got a 1, raise it to the Y. So whatever you get for one equation, just divide it by the other equation, right? So it's pretty much this divided by that, you put in for H2. This divided by that, put in for Br2. This divided by that, put it in for the rate. Okay. And the reason why we picked these two was because we found two numbers that were the same. Looks like my X is just going to be 1. And then if we do, we're going to have to compare 1 and 3. It's the only, all right, compare 1 and 3. Oh, what the heck is 8.25? Oh, 1.15 is bigger. What the heck did you get for this? 1.15, 10 to the 2 negative, divided by... Oh, I'm dividing the wrong ones. I'm lying. 1 and 3. 1 and 3, these two. Well, if you do that, if you take 2.75 divided by this one, then you have to divide this one by that one and this one by that one. Be consistent. But this one, is actually a bigger number. So I'm going to divide it. I'm always going to divide experiment 3 by experiment 1. That's how I'm going to do it. But if you do it the other way, just stick with it. What is that? Yeah, you complete, so you have to get a rate constant too. So, Bonte, if you did it your other way, it'll still work. It'll just looks uglier. This way is easier because you can see that this has to be a 2 because 2 squared is 4. You divide the... I'm substituting everything into this. From one experiment, like to get the rate, divide one experiment's rate by the other experiment's rate. To get the k, divide one experiment's k by the other experiment's k. It doesn't change, it's just k over k. So it's always a 1. So that's why I always just put it there just to, because it's always there. And the h2, one experiment's h2 by the other experiment's h2, but raised to the x. So that's this raised to the x. And then do the same for the BR2 raised to the y. This came from one BR2 divided by the other BR2. I'm doing 1 and 3. Here's BR2. So this guy divided by this guy is 2. And you got to get a rate constant yet.
I tried all 3 of them, right? And then for these 2 I did the same, and the last one I got...
What do you mean, oh, you tried all 3?
To get the k, I tried to solve for k
Okay.
on all 3 of them, and
Okay.
the third one was different than the first 2.
They should all be really, really close. If not, you're messing up your math.
Because the first 2 were like 9.99,
Yeah.
9.99, and then this one was 1.04. Times
Yeah, but 9.999 is really, really close to 1.04.
So
It's the same thing. It's the same thing. You're right. They're gonna be changing a little dinky bit, but not. That's it goes with experimental error. Like look at that 4.18. That should be 4. So it's experimental error. I had to divide in experiment 1 and 3. I had divided one rate by the other rate. Now to get a big number, that's how I do it. I divided the 1.15 times 10 to the negative 2 divided by the 2.75 times 10 to the negative 3. Because 10 to the negative 2 is bigger than 10 to the negative 3. So divide 1.15 times 10 to the negative 2. Now get a rate constant. You're not done until you get a rate constant, then write the full rate law. Did it work? 1.15 10 to the negative 2.
Where do we put that one?
Because it's small. No, it's bigger. 10 to the negative 2 is bigger than 10 to the negative 3. So divided by 2.75. There it is. Okay. Now, if you did it the other way, that's fine. Just always divide experiment 1 numbers by experiment 3 numbers. It's fine. You just have to be consistent. I'm always dividing experiment 3 by experiment 1 because I get big numbers then.
So the X is going to be the first concentration for H2, and Y would be BR2.
Ooh, yeah. Well, it depends on how you write your rate law. You can write rate equals K times BR2 to the Y, H2 to the X. Doesn't matter. A times B is B times A. So, but it just nice to be consistent that way, I guess. K, H2. Okay. So, Vontae, what did you get for K?
9946469907.
Too many digits. 9.9 times 10 to the 9th. Okay. So if you got 1 times 10 to the 10th, or it's really, really close, right? Don't let that confuse you. So we have to put that. Oh, I'm not done. I want to get points taken off. Write your complete rate law. So you're not done until you write rate equals 9.9 times 10 to the 9th. H2. And you could write it, whoa, to the 1, or just leave it empty, right? VR2 to the 2. That, get any points taken off then. Come on. And you can pick any experiment you want to get that K.
After you get these two, what's the next step from here? These two rates.
Okay. Now you know what your X and your Y are, right? You have to solve for your, see here, this is just going to be 4.18 equals 2 to the Y. So you pretty much, Y is going to have to be 2, because 2 squared is 4.
Oh, so you just do this?
Yeah, you find out your Y from this. This one you find out your X. X just has to be 1, because 3 to the 1 is 1, and it has to be 3.
Okay.
Yeah. Yeah, you can. They're going to be a little bit different, but it's going to be really, really close to this. You didn't get that at all? What experiment did you pick?
I picked one and
No, you just pick one experiment to find your K.
Yeah, but like I didn't. Oh, I don't know. I didn't get that because I
Well,
took away
where's
the
your-
credit in the notes. And
Oh, you probably forgot to square it or something.
No, I did.
You did?
Yeah.
Okay.
Let me just see what I did. It was probably my math.
And you got to find your K. You got to write your K in there. I didn't see a K in there. So you have to
No,
divide your rate by
I
these
did.
two.
I had that whole thing and I didn't get 9.9 at all.
Give me 9.9.
It should work. It'll work.
So the 4.18 multiply that just by 2?
Well, you square it.
Oh, you square
And
it.
then you multiply it by 1.2 times 10 to the 4.
Now let's say like Jalen didn't get the 9.9 to 10 to the 9th. This is an exam. Jalen didn't get this. But if she shows all this work, right, it's only 1 point taken off because it's a math mistake. But if I can't see what she did, it's going to be a lot more than 1 point off. So that's why you want to make sure you show all your steps.
Like, it was 10 questions, 10 points each, right?
You show your work. You
Yeah,
get,
that's what I'm saying. Like, I put
Yeah.
all the work here, just my answer didn't come out.
yeah. If I'm looking at yours, it's the exact same as mine. You just got 12 for K. You just screwed up on the calculator, right? So it's just, if you screw up on your calculator, it's a point off. But everything has to be set up right and have to be able to read it. Okay. Monica, what other type of question do you want to see? Boiling point stuff? I think we might have done all those. Let's see if I have any more. How about osmotic pressure? We also haven't done any, before we do this one, okay, we can do this one. But what I want to do is something we haven't done either in the review, and that's like, I remember those questions like, how much time after, for 12% left? All right, how much time does it take for there to be 28% left or something? They have all these words, but 28% left of a reaction. Right? Because we didn't do those in the review either. Yeah, you got it. Well, the 28% left thing, that's one of these. Right? It's one of those. So we should do one of those. Let's do this one first, though. Did you get it to work?
Yeah.
Okay. Mm-hmm.
It's gonna be 9.9 times 10 to the
It's coordinate or progress. Mm-hmm. Yeah, you have to use ATM because that's what big R is in. So have that equation sheet out, and that'll tell you pretty much what you need to do. Okay, now big M is your, that's not molar mass though, right?
But like if it were just asking us for that, we have to.
Yeah, you always have to write units, otherwise you're gonna lose points. So big M is moles per liter. That's what big M is. So hopefully you're not using the one with I in it, right? We're having a help session. If you guys want to talk, I have no problem, but out there. So hopefully you're not using the one with I, right? Yeah, you don't have any choice to convert to ATMs because that's what big R is in. And that cheat sheet. You're gonna have to use it for your big R. Now hopefully this always happens. Don't think big M is your answer. Big M is what? Molarity. Big M is moles per liter. Big M is your concentration. So big M is not your answer. It's not molecular weight. See, we're not sure of how to attack this. Try not to be looking in your notes. Do you see how to do it? Okay, that's good. And then you're going to put this in for here. Good. In Kelvin. Yeah, and you're going to get your big M. Okay, then what are you going to do with the big M? Yes, you're going to use the big M to get moles. Because big M, use, what is it? This, right? Molarity, right? So you're going to know what big M is. All you have to do is solve for this one. So you put in the number for big M, put in the number for total liters. There it is. Put that into liters. And then solve for M, moles. That's exactly it. Oh, it's big because of, we mentioned it only once, I think, the word polymeric. Expect a huge answer. Otherwise, you're right. You should be looking at that thinking, oh, I screwed up. Good. So Ashlyn was telling me a really good game plan. If you didn't catch it, right? If you're not sure where to go. She got this into atmospheres, right? She's solving for her big M, and then she's going to use that big M equation to get moles. Solve for the moles, put it in for molar mass, because molar mass is grams over moles, right? And that's how she's going to get her answer. How do you get the moles? You use the big M equation, because you solve for big M. Now I use the big M equation. Big M is moles over liters.
Multiply it by molarity, which of what you solve for. Which is this? No.
It's an ATM. How do you solve for moles? That's what I'm asking. Molarity moles over moles. Okay, that's what
Okay. So did you get this far? I got my big M. I know my answer's molecular weight. I have to divide the grams by the moles, and they told me the grams part, I just got to get the moles. So to get the moles, set up your big M equation. If you don't like multiple steps, you could just set up the big M equation right in here and save yourself a step. Because you know big M is moles over liters of solution. So you could just put it in right there, save yourself a step. But it's the same thing. .031.
Yeah, and then you plug it in into that. For this one, did you get Dr. Smith said 4.41?
I don't know. I made up all these numbers. You just see what other people get. What'd you get for moles? Yeah. .2 times 10⁻6.
8.46 times 10⁻6 divided by, or multiplied divided by
Okay. I got 2.2 times 10⁻6 for the moles. And then put it in for your moles and hopefully get a big number like 14,000 grams per mole. Yeah, somewhere around 14,000, 14,100, something like that. Sure. It always looks more scientific. Somewhere around 14,000, depending on how many digits you carried through this whole mess. All right. Everyone okay with that? Okay. That's my suggestion is to try some of those that we where's all that kinetic stuff? What's that? I can email it to everybody. It's on. It will be. It's being recorded. Here's one. Yeah, I can put it on there. Yeah. It's gonna be super long. I don't know. It may not upload. We'll find out. I can't. We're talking like hundreds of megabytes. But I can email the document. The problems. Do you want the document with solutions or just the document blank with the solutions? Okay. Uh-huh. Oh, nice. Nice. Yeah. Yeah, that would be useful. Okay.
She would give us the problems. That's one day, and the next day she'll put up the answers. So just have to work it out by herself.
Oh, good. Yeah, the answers aren't right there for you right away. We've got cyclobutane, first order. Initial concentration is 0.0015. I think we just did this in something like this in class. Has anyone started this one yet? This isn't the one. No. Let me switch gears then. I want to do something like this. This is more to the point. Okay. There's a reaction. They want to know what the half-life is. You want to know what the half-life is. So we got to pick an equation here. What would be the equation? Yeah. You see it? T1/2 equals 0.693 over K, right? Okay. Now that little half-life, T and K have to be in the same units. So that's how you're going to report your answer. Your answer will be reported in what units then? Seconds. Seconds. So part A isn't the confusing part, I don't think. I think it's part B. Oh, 2 times 10 to the negative 6. What did you get? 96,000? Oh, don't go to hours. Just leave it in seconds. It didn't care, did it?
Yeah.
Oh, it does say in hours. Oh, what that sucks. 693. 693. 346,500 seconds. Yeah, I get that into hours. Did you get like around 96 and a quarter or so? Kelly, did you get that? Or am I going too fast? Should get around 96 hours, right? Hopefully the first part you got. It's much more straightforward than the next one. Now on this next one, 25% left. There's an easy way and a hard way to answer this. Does anyone see what the easy way is? What's the easy way? I think that's, well, the thing to is 25%. If I'm just used to seeing a half is what percent? 50%. A fourth is what? 25%. And you know what I'm doing? I'm just keep multiplying a half times a half times a half. Because this is a half times a half. Right? In fact, 1/4 is how many half-lives? 2. So to get the answer for 25% left, you could just multiply by 2, right? But that's a special case. I prefer doing it what someone was getting into, just doing it that way, because it'll always work. Because who wants to memorize all these? All right, what's an eighth? What is an eighth? A half times a half times a half is an eighth. Do you know what decimal place that is? You want to memorize all those? I think it's easier just to calculate it, right? Use it as, someone said the concentration of A at time t. Use it as that. So, because how many hours would be required? What symbol are you after? You're after t. We're going to find t. Okay? And what equation are we going to be using? ln, well, with the symbols though. ln of A at time t all over the initial equals negative kt. Okay, we're going to use this. Then you have to memorize all these decimals. Okay? So let's do the 25% left one. Let's say you didn't realize, oh, okay, that's actually a fourth, 2 half-lives, memorize what to do with it. This is 25% left. So 25% left, what would I put in for AT then? There has to be 25% left. if I have 0.25 times the initial, whatever. Think of it this way: if I have whatever percent left, just take whatever the percent is times the initial. It always works that way. They want to know what percent is left. Well, whatever that percent is, put it times the initial, and that's your answer. That's that percent left. If they said 50% left, if I have 12 cookies, 50% of them are left, you multiply by a half. So that's 0.5 times the initial amount. So same thing here. You'd have the natural log of the 25% left. You have to move the decimal point, though. That you have to remember. Everything else stays the same. Here's our initial, negative KT. And our initials are just going to cancel out on you. And then take the natural log of 0.25, see what number that is. They told us what K was. So, well, actually a negative K. Divide both sides by negative K, you'll have your T. Okay. So it doesn't matter what percent left they say. Just put the percent in here times the initial, and that's the percent left. So like 18.9%, move it over a couple places, put it in front of the A0, and do the calculation. It always works. You don't have to memorize an eighth is 0.125. What was K? 2.0 times 10 to the negative 6. Okay. Now they want the answer in hours, though, so you're going to have a little extra work. Yeah. You divide by 3,600. Or divide by 60 twice, however you want to convert. Oh, you can do it that way. You can do it that way. I have no qualms with that. That's how the book actually wants you to do it. But it seems to me, I don't like to memorize anything. I would rather just always do it this way. I don't have to think. Because 24th, that 25%, that's a special one. That's a half times a half. Yeah, it is. It's easier, but that's if you remember all those fractions. And it won't work for something like 18.9%. All right? It won't work for this one. So this way will always work. I got about 192 hours. It would have been easier just to multiply by 2. Right. But it won't work for the 18.9%. So you have to do it the long way for the 18.9%.
What you do is, so we take the natural log of this.
You take the natural log of 0.25 and you get a number. And then you have to divide both sides by this. Bring it over here to solve for the t. No, because it's the natural log of whatever's inside the parentheses. Right? The natural log of this equals something. So take the natural log of this 0.25. And then whatever you get, divide it by that number, and you get 693,147. So the 18.9%, the answer is 231. Okay. For the 18.9%, Monica got, what was it again? What did you get again? 231 hours? Okay. So if you, in a similar way, the answer to this one is 231 hours. Several folks got it. This should be easy points. R20 should be easy points. If something like that is on the test, you should be really excited that that's on the test. All right? Make sure you know how to do something like that. Because if that shows up, that should be easy points. So take 0.25 ln, 0.25 natural log. Okay, now divide by 2 times 10 to the negative 6. All right, divided by 2 times 10 to the negative 6.
But don't you put negatives in front of the 2 points?
You can, doesn't hurt, yeah. All right, it works. Yeah.
We keep getting this. Did we do something wrong?
For the 190,
hours.
for the,
The amount of hours.
instead of getting 192,
Instead of getting the 231.
instead of getting the 231. Oh, I didn't do that one. All right, you should be taking the natural log of 0.189.
So that's what.
0.189. 0.189.
0.189.
There it is.
Okay.
0.189. You got to change the there it is. You got it. Okay. What other type of, I think we've covered all the ones that I think are really tough. There's something you'd like to practice more on? Oh, might as well finish this. How about R20? In R20, what does the negative 359 kilojoules per mole have to do with anything? Makes it exothermic. That's the only reason why it's there. Right. So you make sure you draw an exothermic potential energy diagram. Right? So those products have to end up heat. So products are going to end up really low or end up really high? Really low. Right. Exactly. Your products got to end up way on the bottom. Products down here, reactants up here. Right. So here's your reactants. Here's your products. Right. Whatever we did in the homework and in-class problems. Yeah, freezing point, boiling point is much more common. We hardly ever did, I don't think. Right? Vapor pressure stuff. Here's this question. Here's another kinetics question. What type of problem do you... We haven't done any concentration questions. Like, how would you prepare? Remember those? Let's see. Here's one. Well, how much water should be added? It's kind of a how should you prepare. Right? That's kind of a how would you prepare question. Because you have 75 grams of this fructose, so how much water do you have to dump in there to get 5.5? Little m solution. So what equations? There it is, right? And where's your answer in this? Where's your answer? Yeah, there it is. Yeah. And they didn't care what units your answer in, right? So just give your answer in kilograms. Notice how they didn't care your units for water. So just leave it in kilograms. If you're Jalen's question, if you see what her question is, you're doing this right. She said, "Can you leave it in kilograms?" That's a big hint as to how she's doing the question. She picked the molality equation, and she's just substituting in. And then you got what is an answer?
Do you cross multiply these or divide these? I think I might have done it wrong.
You have to, top to bottom, have to multiply.
Multiply, if I did it backwards.
Because it's going top to bottom. The diagonal. Yeah. Oh, we do have to convert, don't you? Those 75 grams into moles.
Is it like this? Because that's a total?
It's kilograms of solvent is in the bottom. Moles of solute is up on top. They told you the, okay, good. The cm is the 5.5, right. But look at the moles of solute. You just have to convert those 75 grams of that funky compound into moles, and that will be the moles of solute. You're solving for the bottom part.
So they gave me the mole. They gave me.
Yeah, because notice that G, 75 Gs, right, of fructose. So where you messed up is you didn't recognize the solute and the solvent. Yeah, the solvent has to be the water.
Because I was like, how much water should be added? So that.
Yeah. Yeah, I can see that. I can see. Yeah, the English does make it sound that way. Yeah. Oh, but there's going to be a lot more than 18
No, I know.
grams.
I was thinking water.
You have to, yeah, 6 carbons, 12 hydrogens, 6 oxygens. Yeah, whatever you get, that'll be your moles. You put that up here. You got it. Yep. Okay. Did anybody else get 156 for the molar mass of that fructose? No, for the molar mass. Add up 6 carbons, 12 hydrogens, and 6 oxygens. 180. 170. 6 carbons, 12 hydrogens, and 6 oxygens. All right. 12 times 6 plus 12. Well, that's 6 times 12. Yeah. 6 plus. Yeah, about 180. About 0.42 moles. All right. So we got the 0.42 moles. So that's Cm, 5.5 has to equal 0.42 all over kilograms of water. All right. What we want is on the bottom. Remember the diagonals. Boom. Move up where the 5.5 is. Move the 5.5 down. About 0.076. All right. This looks like a good one. I mean, they're all good questions, but if you have some more energy. Okay. So this is kilograms of solvent, right? This is our answer. That's going to be how much water. This is the amount of solvent. And they didn't specify the units, so just leave it in kilograms. So realize top bottom, right? Top bottom, top bottom. Our answer's in the bottom. You got to get it to the top, either this side or that side. It's a lot easier over here. Just move it along. All right, bring it up here. And then bring the 5.5 down this diagonal down there. So you end up with 0.42 divided by 5.5. Yeah, I'd say this 13 is about as ugly as it can get, one of those freezing point questions. Not sure where to start on 13. Okay. Yeah, so we're going to solve for CM, right? And they want to know how many grams of urea. So if we can figure out the moles, convert the moles into grams, we'll have it, right? Because you have the moles. This guy convert moles to grams, and it'll be there. Yeah, it's the change in the freezing point. So it's just going to be the 0.085 is all. You're right.
Just divide by the K.
KF, and you'll get the CM. And then set up your CM equation, solve for the moles, then you know what the formula is, so you can convert moles into grams. CM is moles of solute over kilograms of solvent. So we'll solve for him, then we'll convert into grams.
So I get the weight or whatever,
Yeah.
multiply it by 2, and then I add C,
Yeah, yes, you're going to have 2 N's, 4 hydrogens, a C, and an O. Yep. I don't know. Okay. So what we're going to do is we're going to use that delta TF equation, right? Because it's this freezes thing. And then, let's see here. Let me see if I can make this little, hopefully I see everyone using this. Right? Except the answer is how many grams of urea. So why don't we just keep messing with this? There's nothing wrong with it. Right? And recognize our answer staring right at us. Right? Just convert to grams. Right? It's a freezing point problem. So delta TF equals KFCM. And it's definitely, you don't see a metal, so don't use the I problem. And they're after grams of urea, grams of solute. So I just kept substituting in. Okay. So this way I can kind of skip that step of solving for CM and just solve for moles right here. It's the same thing, but it might be a little bit more straightforward. So that means I have to know what delta TF is, KF, and kilograms of solvent, and I'll solve for the moles. Not quite done. I have to convert it into grams, but I can do that. Okay. So how much did the freezing point change by? Oh, 0.1. Right? Solve for the moles. About 4.6 times 10 to the negative 3. Oh, I should do this in a different color. All right. So I just got to get it into grams. So okay, now what did you get for the molar mass for 60? So that's 2 nitrogens, 4 hydrogens, a carbon and oxygen. 60. Okay, great. Yeah. About 0.27. Okay, about 0.27. So if you did that problem without looking at anything but your equation sheet, you're in pretty good shape. Oh, Gloriana said that the molar mass was 60. So she added up 2 nitrogens, 4 hydrogens, a carbon, and an oxygen. That's the molar mass of urea. Did you get 60? She got 62. Did you get 60 or 62? 60. What is it not working? Okay, so realize I'm really used to recognizing what's on top on the bottom, right? So I'm going to solve for him. So it's going to be dividing by, taking the 0.85, dividing by this, and then times this. And I'll have my moles. So 0.085. Well, yeah, but moles can't be negative. So pretty much just drop the negative sign. Yeah. Because you're right, it is negative because it dropped down by that much, but. Well, 0.085. Divide by 1.86. And then times 0.1. So divide by 1.86. Times 0.1. Yeah. 4.6 to 10 negative 3. Well, I just rounded. What else is in here? There's that type of question. If you still have more energy, I have kinetics problem we haven't done. A bunch of concentration questions. Probably the most difficult question. Have we done anything like this? This was way in the very first day. Do you remember doing stuff like this? Like, look at this number 3. This was from a long time ago. How much heat is needed to boil 20 grams of water initially at 50 degrees Celsius? We don't even have equations for it. That was from a long time ago. Do you remember how to do this? We might have to. Okay. Okay. There's 2 ratios here. One of them has a temperature in it, the other one doesn't. Now first think of it this way. Heat, what are the units of your answer? Kilojoules or joules, whatever one is easier, right? Joules or kilojoules. Here's one that doesn't have a temperature in it, the 46 kilojoules per mole. What would you use this ratio for? That's the energy necessary to what? To vaporize it, to boil it, right? But for it to boil, it has to be at what temperature? 100. But back up a little bit. This is the energy for it to boil, 46 kilojoules. If you have 1 mole, it would take exactly 46 kilojoules. If you had 2 moles, well, twice that amount. So you need that. That's the energy to get it to boil. The one over here the kilojoules per mole degree Celsius, that's the energy necessary to get it, to heat it up to the boiling point, right? So there's kind of an equation, but there kind of isn't. You just kind of work with it to get units to cancel, so you get kilojoules. So our answer is really going to be, our heat is going to be, right, the heat, you know, to boil the thing, and the heat to, you know, get it to 100. You have to add those 2 kilojoules up, and that's your answer. So the heat to boil, you use the 46 kilojoules per mole to get that one. The heat to get it up to 100 in the first place, use the 0.075 to get it up there. Yeah, you have to convert the grams to moles because it's per mole. So to get those moles to cancel, yeah, you have to convert those 20 grams into moles and multiply it by this guy to get the moles to cancel. And you'll have it. Exactly. So this very first one, you'd have 46 kilojoules per mole times, you got to put in the moles. All right? Just convert that guy into moles. All right? Convert them to moles. Now the next one's a little bit uglier, because not only do you have to cancel moles, you have to cancel Celsius. All right, see if you remember how to do that. And a lot of folks are getting 1.1 as the moles, right? Just got to get that second kilojoules, and you'll have it. You're going to have to multiply it by the moles again. And then you multiply it by how many degrees Celsius? 50. Because that's the number of degrees you got heated up by. Right? Kind of like delta T. My moles cancel. My Celsiuses cancel. What did you get? 55? 55? Anyone else get 55? 55. Mark got 55. Oh, 55 it looks like. So if you want to make sure you understand what you're doing, R2 is pretty much the same type of question. Same type of idea for R2, except, there's not a two-step thing here. You have to add two numbers up. Mm-hmm. Mm-hmm. So you have to add them up. So it'd be this times that, and that's supposed to be 46. Is that a 46? What is that? No. 46 kilojoules per mole. So you got 60 as the molar mass of isopropanol. Yeah, two people got 60 for the molar mass of that stuff. So in R2, yeah, I would convert those 2.25 grams into moles. And then once you did that, all right, convert this guy into moles. All right, then convert to kilojoules using, boom, that ratio. Right? Because the moles will cancel if you multiply them, and if you have 42.1, don't flip them or anything. Leave it at the 42.1 kilojoules up on top, and just multiply it by the number of moles, and you'll have it. I think some people said it was 60 as the molar mass. You can just keep going. And then in a mole, 42.1 kilojoules. Around 16. Anybody else get around 16? 1.37. Got about 1.6. 1.6? Yeah? G 1.6? Oh, okay. 2.25 divide by 60 times 42.1. Because my grams cancel, then my moles cancel. I'm in kilojoules. You don't divide by 42.1.
No, like
2.25 divided by 60 times. Yeah.
that. And I divide it.
No, it's times. Look at your units. If you divide, your moles aren't going to cancel. Your moles and units won't cancel. How about, here's one of the last questions I have, really. Just making sure you can read these. Estimate the boiling point of water at 1 atmosphere, 500 millimeters of mercury, and 200 millimeters of mercury. How did this work? This is, again, from a long time ago. Oh, can I make the diagram bigger? Oh, yeah, I should be able to if I click on it, right? There it is. Okay. 1 atmosphere, 500 millimeters of mercury, and 200 millimeters of mercury. What are the boiling points of water? What would you say for 1 atmosphere? Yeah, go across that. The diagram's in millimeters of mercury, so you just have 1 atmosphere is how many millimeters of mercury? 760. So yeah, right here, that's 1 atmosphere. So go straight across and down 100. Okay. How about 500 millimeters of mercury? Here around 90. Yeah, I would guess somewhere around 90 too. Somewhere down here and down. 200. At 200, go across. Yeah, I don't know, 65. That would be good. Right. Okay. So as the pressure goes down, the boiling point goes down. Okay. So I'll be here bright and early on Monday.